Well, hello again, my virtual friends. Last Sunday, I happened to be out at school for the first time since all this chaos started, and I went into my room, and one of the things I noticed is that my Simpsons calendar up by the Pepsi stuff still said March. And so, of course, I had to switch things over and show you what April looked like on that calendar. Now, I didn't go out to school just to look at the Pepsi stuff or to show you the calendar. I wanted to get a couple of specific pictures that go along with our next chapter that we're going to be looking at. You guys should be familiar with that table of goodies that I have over by the Pepsi stuff. And you've probably seen a lot of these things that you're looking at. There's some of them I use periodically for educational reasons in different classes, especially in geometry and statistics. Today, though, we're going to look at one of the objects that fits right along with our next chapter in advanced algebra. And that would be this thing, which I sometimes will joke about as being the world's simplest 3D puzzle. All it is a cone that's been sliced up in different directions, and there is a reason why that goes along with what we're talking about in this chapter. So the chapter that we're going to be starting this week, and realistically probably looking at for most or possibly all of the rest of the year, deals with what are called conic sections. Conic sections get that name because they literally are sections of a cone. There are shapes that you can get by slicing a cone in different directions. If you look at the right-hand picture, you can kind of get an idea of what some of those shapes would be. The four main conic sections are circles, parabolas, ellipses, and hyperbolas. The first two of those you should already know some stuff about. You guys know what a circle is. Most of you studied circles about this same time a year ago in geometry class. And we'll get into reviewing more about how circles work next week. Parabolas we mostly studied earlier in the year. And they also are shapes that you can get from slicing up a cone. The other two shapes are an ellipse, which is basically just the formal mathematical name for an oval or egg shape, and a hyperbola, which kind of looks like two parabolas side by side. It always has two parts to it and makes sort of a mirror image. So one thing I do want you to know this week is that the four main conic sections are circle, parabola, ellipse, and hyperbola. This picture is just showing you how you could make all of those conic sections by slicing up a cone or two cones that are sort of nose to nose, point to point in different directions. It turns out that a circle you always get by going perpendicular to the axis of a cone, and a parabola and an ellipse you end up slicing diagonally across it. Depending on how far diagonal you go, that makes the difference as to whether it's a parabola or an ellipse. A hyperbola, to get those two parts, what ends up happening is you slice straight up and down in the same direction as the axis of the hyperbola. And we'll talk about all of those in the next few weeks as we go through the rest of the topic. So the conic sections are literally parts of a cone, but they can also be defined another way, and that's using the idea of distance. This spring, of course, we've heard lots of stuff about distance. You talk about social distancing and not spreading the disease, and the reason that we haven't been able to be at school is that we're supposed to be doing distance learning. But the distance we deal with in conic sections really doesn't have to do with either of those. We're talking about geometric distance, and well, the definition of distance says that it's the amount of space between two things. That's basically what we're talking about here, how far apart things are. In math, we most often deal with distance using what's called the distance formula. This is something you very likely came across in Algebra 1, although depending on how things went at that time of year, you might have rushed through it real quickly or not really remember it. The distance formula says that you can find the distance between 2 points, d, by taking the square root of x2 minus x1 squared plus y2 minus y1 squared. Now people will often look at that formula and it just starts blending together because it looks like a lot of variables and a lot of stuff going on, but really it's pretty straightforward. All the distance formula is just a fancy way of writing the Pythagorean theorem. You should remember the Pythagorean theorem was how you could find the hypotenuse, the longest side of a right triangle, and it usually was written a squared plus b squared equals c squared. If you take each of the legs and square them and add them up, you end up getting the hypotenuse squared. Well, I've got a picture here that's got 2 points labeled x1, y1, and x2, y2. All the x2 minus x1 in that distance formula is just like the length going across. It's like the bottom of this triangle. Y2 minus y1 is just the vertical distance. It's how far it is up and down. And so all they're really doing is taking those sides, squaring them, adding them up, and you end up having the distance formula. Again, the formula says x2 minus x1 squared plus y2 minus y1 squared square root. Sometimes, though, it's easier just to think about what you do than to worry about the formula itself. What that formula is saying is that I subtract the x's, the first number from each point, and then I square. Next, I subtract the y's and square. I add those things up, and I take the square root to get my final answer. Subtract the x's and square, subtract the y's and square, add them up, take the square root. We're going to look at a couple of kinds of problems that involve the distance formula. The most common, and really the easiest, just say this. It says find the distance between a couple of points. Here we've got find the distance between the point negative 2, 7 and the point 6, 1. This would be saying if I graph those points and I measure diagonally, exactly how far would that be? So of course we got to haul out the distance formula. I've got to subtract my x's and square, subtract my y's and square, add them up and do the square root. And you notice I plugged in here, I've got the square root of 6 minus negative 2 squared plus 1 minus 7 squared. Now I'll tell you, it doesn't actually matter what order you subtract in. I could have done negative 2 minus 6 squared and 7 minus 1 squared. The worst that's going to happen is you'd get like a negative instead of a positive, but when you square, it all ends up positive anyway. So the order doesn't matter. What does matter is that the x's have to go together, the negative 2 and 6, and the y's, 7 and 1, have to go together. Here I'm just working that out. When I take 6 minus negative 2, I get 8. 8 squared is 64. 1 minus 7 would be negative 6. You square that and you get 36. If you add those up, we've got 100, and the square root of 100 is 10. So the distance between these 2 points would be 10. Here's a real similar question. Find the distance between 3, 8 and 6, negative 2. We're going to do things pretty much the same way, except this time I'm pretty sure it doesn't come out even. Again, just like before, what we want to do is plug in the numbers where they belong. I've got to subtract my x's and square, subtract my y's and square, add them up and do the square root. So 6 minus 3 squared plus negative 2 minus 8 squared. I add those up and we're going to do the square root. When I work things out this time, I'm going to have 3 squared, which is 9, negative 10 squared, which is 100. You add those up, and honestly, what I would probably write for the answer is the square root of 109. You can do problems like this on your calculator. I have a couple of screenshots here. The one on the left would be from a TI-84, and the one on the right is what I always put when I'm doing things from a TI-83. And you notice that both times it's giving me about 10.44. Well, if you take the square root of 109, you get about 10.44. So it's just the same answer written a different way. If you do have like the TI-83 that I have or an old cheap calculator, you got to be careful of parentheses because everything under the square root's got to be in parentheses, and then each of the things you square is in parentheses. It's okay on problems like this to write a decimal. It's also okay just to write the square root of 109. I usually just do the square root of 109 because personally I think that's easier, but everything you're looking at here would be right. And again, your basic process for finding the distance is take your x's, subtract them and square, take your y's, subtract them and square, add all that stuff up, and then take the square root of that answer. We're going to look at one other kind of problem today. This time, it tells us that the distance between a couple of points, A and B, is 5. And they tell us that point A is 7, 2, and point B is x negative 2. So I don't know what the x is for B. And the question is, so what is it? What would that number have to be? And so again, what I want to do is take what I know and plug it into the formula. This time I know the distance, and that's why it says 5 equals at the beginning. I don't know the second x, which is why I just put x minus 7 squared in the first part of that square root. Then for the y's, I did negative 2 minus 2 squared. What I want to do is simplify this as much as I can, and the first thing I did is I did negative 2 minus 2, that's negative 4. If you square that, you get 16. The big step that's different from just finding distance is the next thing I did is I squared both sides of the equation. I took 5 squared and got 25. And then when I do the right-hand side of the equation, if you take a square root and square it, all that happens is you're canceling out the square root. So I just put equals all that stuff that was under the root, x minus 7 squared plus 16. And now what we've got to do is solve what's left. So what I did is I took 25 minus 16 and I got 9 equals x minus 7 squared. Problems like this, you're typically going to get two different answers. And that's because the next step that we had to do was to take the square root of 9, which gives you plus or minus 3. That cancels out the squared on the other side, so plus or minus 3 equals x minus 7. Now what I'm going to do is I'll take positive 3 plus 7, that gives me 10. Negative 3 plus 7 gives me 4. So x could be either 10 or 4. Those are both correct answers to this problem. So here's one last example that's kind of like the last one. What we're supposed to do is figure out y, but it tells us the distance between A and B is 11, A is negative 5, 1, and B is 3y. So we've got to take that information and see if we can find what y is. And again, the first step is plug things in where they belong in the formula. I know the distance is 11. I subtract my x's and square, and when I subtract the y's, it's just y minus 1 squared. And here I've got all the rest of the problem worked out in one place. Again, what I want to do is square both sides. 11 squared is 121. And then on the other side, I also simplified that 3 minus negative 5 is 8. 8 squared is 64. So 121 equals 64 plus y minus 1 squared. Now to finish it off, I subtract 64. I've got to take the square root, and then I've got to move the 1 over to the other side. So that's why my answer would be plus or minus the square root of 57 plus 1. And I would just leave the answer exactly like that. So you've got several problems you can use to practice with distance formula and finding points if you know the distance. And of course, you'll have a quiz coming up this week that will be over that. Then next week, we're going to start talking about what does that have to do with all of these shapes that we've learned with circles, parabolas, ellipses, and hyperbolas. And we'll tie them all together and talk all about conic sections. So you guys have a good week, and we will see you later.